Welcome to the 8th lecture about parallel programming with OpenMP and MPI. Today we're going to dive into the message passing interface and give you a brief introduction to the basic MPI toolbox. The message passing paradigm deals with distributed memory computer architectures. This means that each process or each processor can only access its own dedicated address space. This doesn't mean that there's no shared memory architecture in the system. It only means that we don't explicitly exploit it. So processes in the system may still be sharing memory, but the programming model, the distributed memory programming model, does not see that right away. There's no global shared address space. All the data exchange, all communication, all synchronization is done explicitly by passing messages through some communication network. So a message has to be passed by handing it to some library or some communication mechanism and sort of offload this communication to some other instance. A message passing library, if you want to use it, should be flexible, efficient, and portable. Portability is actually the main concern because we want to run a parallel program that was developed and optimized on one system more or less as effectively on a different system. That also means that abstraction is key. We want to hide the communication hardware and software layers from the application developer. You as a developer should not be concerned with what is the actual hardware used to implement the communication network, for example. This is all abstracted away. The widely accepted standard in high-performance computing and numerical simulation is the message passing interface, or MPI. MPI follows a process-based approach. Actually, it's not strictly necessary if you look into the standard that MPI tasks are processes and the standard chooses a particular wording, but for the time being, we can imagine an MPI program consisting of several processes, which means, since we're dealing with processes, all variables are local. There's no concept of shared memory as we have it in OpenMP. It's also a basic principle of MPI that the same program is running on each processor, each machine, each process runs the same binary image of the program. We call this SPMD, same single program, multiple data paradigm. The program itself is written in a sequential language. This is also different from approaches like OpenMP, where the base language like Fortran or C or C++ is augmented with compiler directives or other language features. In MPI, the program is actually a sequential program. All the parallelism is built into how you call the message passing library. Data exchange between running processes is done via sending and receiving messages using the MPI library. There's no automatic workload distribution. That's another difference to OpenMP. In OpenMP, if you have a loop, a simple loop, you can just write pragma OMP parallel 4 and leave it to the OpenMP runtime and the compiler to do the work in parallel. There's no such thing in MPI. You have to do it all by yourself. The MPI standard is maintained by the MPI forum. It defines the standard and its library subroutine interfaces. The latest standard is version 3.1, which was released in 2015. It's quite a chunky piece of work. It has 868 pages. You can buy it for I think 17 euros from the High Performance Computing Center in Stuttgart. Version 4.0 is under development or has been under development for quite some time, and it's an actively developed standard. There are a lot of hands on this standard, and it's a major effort to drive it forward. So there are approximately 60 members in the MPI standard forum. They comprise application developers, research institutes, computing centers, manufacturers, and software designers. So it's a very broad forum, and a considerable amount of people hours goes into the development of the standard. There are luckily successful free implementations. The most popular one over the last 20 years, probably MPI-CH. There's also MV-APITch, OpenMPI, and some others. And there are, of course, commercial vendor libraries by the major companies like Intel, Cray, and Hewlett-Packard. The standard is free for download at mpiforum.org, but as I said, you can also order it as a printed book. I've already mentioned that portability is the main goal in the development of the MPI standard. We want to write architecture and hardware independent code. So we have the hardware, which could be quite diverse, comprising different processor architectures, network hardware, and so on. There are drivers, of course, that take care of the basic functionality, sending messages back and forth, for example, and implementing the basic functions we need for the upper layers that deliver messages. MPI is the library layer that you deal with as an application developer, and your application is built around that. So ideally, your application should never have any connection to the actual hardware or driver layers. However, some parts of MPI allow you, for optimization purposes, to access some aspects of the lower levels, just to make some operations faster or more efficient. MPI is defined with Fortran and C bindings. C++ bindings were deprecated some time ago because it was recognized that they were rarely used, because C++ programmers tend to build their own abstraction layers around the C interface of MPI, so it wasn't considered to be necessary to further maintain the C++ bindings. MPI has some interesting features that support the development of parallel libraries, and we'll come to that, of course. And it also supports heterogeneous environments. This is a feature that's built into the innards of the MPI standard, and you see it all the time. So with MPI, for example, you can run parallel programs on clusters with compute nodes of different architectures, very different architectures. You could even run MPI programs comprising compute nodes in several computing centers at the same time. So this flexibility is built into MPI from the start. Okay, so let's dive into the details. First of all, some words about the architecture of MPI. From the operating system's point of view, an MPI program is just a bunch of running processes, so it's no different from any other collection of processes running on the system. The developer's view is different. The developer deals with library routines for coordinating those processes, communicating between those processes, and synchronizing those processes. The user's view, so a user is someone who starts an MPI application that's already compiled and linked. The user's view is the execution environment of the MPI implementation. So how are resources allocated? How is the parallel program actually started? Who cares for starting the processes that comprise the parallel program and other implementation-dependent behavior? So the user's view is more comprehensive than just a library. It also contains the MPI execution environment, which can be important, as we will see. Now, in an MPI program, a number of processes, usually a constant number of processes, runs throughout the program's execution. So in this diagram, the black arrows are like timeline arrows for processes comprising the MPI program. The MPI startup mechanism, so how the processes are launched and connected to each other so that they know they're part of an MPI program, this is something that establishes a kind of context between those processes. And this context is called a communicator. A communicator is something that we will come across very often in this course, so we'll deal with that a lot. Now, once those processes are running and know that they are part of an MPI program, there are two generally distinct ways to deal with these processes, to communicate between these processes. And the first one is point-to-point communication. Point-to-point communication always happens between pairs of tasks or processes, so there's a message going from one process to the other. In contrast, there's also MPI collective communication. This is something that happens between all processes in the program, or maybe all processes in a subgroup of the program. Examples are barriers, reductions, scatter and gather, and you know some of these terms already from the OpenMP context, where we also have barriers and reductions. In the end, of course, the parallel program must be shut down, and MPI takes care of that. Specifically, the execution environment, not only does it care for proper and well-defined program startup, but also for shutting the program down in a well-defined way. As I mentioned in the beginning, MPI has C and Fortran bindings defined. So if you want to use MPI in a C program, you have to include a header file called mpi.h. In Fortran, so the old style Fortran 77 language, you include an mpif.h file, and in Fortran 90 and above, you use a module which is called MPI, or with Fortran 2008 and above, MPI_FO8. Once you have these headers or modules included, you can use the functions in your program. The way you call the functions is a little bit different between C and Fortran. In C, most of the MPI functions return an error code as a return value, while in Fortran, the return value for the error code is part of the argument list as an output argument. Also, as you know, in Fortran, the calling convention is that function names and subroutine names are not case sensitive, while in C they are case sensitive, and they always start with uppercase MPI underscore, and then one uppercase letter, and then only lowercase letters. This is the convention for MPI functions in C. Again, in Fortran, it doesn't really matter. In MPI, there are a couple of global common constants. In C, they are also all uppercase. Remember always the basic difference between array indexing between C and Fortran. In C, we index all arrays from 0, and in Fortran, we index from 1. This is important, especially when we deal with indexing within MPI, where sometimes the way MPI does it goes against the wisdom that's built into the base language. The details of how an MPI program is actually started are implementation defined, and we'll come to an example later. Whatever you do, the first call an MPI program before any substantial work is done, which means usually after the initial declaration of some variables, is a call to MPI init. MPI init initializes the parallel machine. In C, it requires access to the command line of the program by means of pointers to the argument count and argument vector, which means some implementations will use these pointers to modify the actual program's command line. The last call in an MPI program should be a clean shutdown of the parallel machine. This is done via MPI finalize. After MPI finalize, not all processes are guaranteed to continue, only the master process. So number 0, as you will see later, they are numbered just like OpenMP threads are. Only the master process number 0 is guaranteed to continue after finalize. This does not mean that the others will always die. So it's just that only 0 is guaranteed to continue. In other words, you should not make any assumptions about what happens after finalize, and it would be best to just terminate the program after you return from finalize. If you print anything, if you pipe anything to standard out and standard error within any MPI process, the usual implementations, the standard implementations, redirect that to the console where the program was started. So this is actually desired behavior, but it can backfire if you use it too much, because it also takes a lot of time to write stuff to the standard out and standard error. Also, some implementations have flexible options as to where to direct the output. So this is also implementation defined behavior that you can look up in the documentation. Now, what happens when MPI init is called is a so-called communicator is set up. And this communicator is called MPI com_world, which is a predefined symbol in MPI. MPI com_world is like a synonym, a phrase for all processes that comprise the MPI program. Later we will learn that you can actually split off subcommunicators and make groups of processes that have fewer processes than MPI com_world, but MPI com_world is something that comprises all the processes. Now, within the communicator, processes are ranked and are ID'd by a so-called rank, which goes from 0 to number of processes -1. In the same way that OpenMP threads are numbered from 0 to number of threads -1. So pretty much the same concept. Now, this communicator and its set of processes, so MPI world means all processes, is defined at the beginning. Within the communicator, we have the rank, and of course the rank is the basic feature of MPI that lets you decide what a specific process should do. So in order to obtain the rank of a process, you call a function MPI rank. The rank is an output argument in the argument list. So this is something that you have to get used to with MPI. You would expect that in a C library, you would get the rank as a return argument from the function, but the return argument for most MPI functions is actually the error code. So we have to find a way to return values without using the return value. So this is done via handing the address of the rank variable to the MPI rank function. And this is a very common pattern with MPI. Now remember that MPI world, even though it comprises all processes, it's not the only communicator that may exist in a program. So if there are multiple communicators, one process may have different ranks if it belongs to different communicators at the same time. And this is entirely possible and also useful behavior, as we will see later. Of course, when we get the rank, we also have to know how many processes are there, and this is done via MPI size. Again, the size argument is an output argument. You have to supply the address of a variable here, and what you get is the number of processes in the communicator. You also see a typical pattern here. Most MPI functions require a communicator argument in order to tell which group of processes, which communicator is actually meant. So with that, we can already write our first program in C, parallel program, typing hello world to the console. It's a complete program, so you can try it out right away if you want. We have to include the header file. This is C, so it's mpi.h. We need variables for rank and size. And the first thing we do after the declaration of variables is the call to MPI init. And we supply the address of argc and the address of argv to give the implementation an opportunity to modify the command line. After that, we obtain the size of the communicator, so the number of processes, and the rank of the current process. Remember, an MPI program is a bunch of running processes. All have different process IDs, all have different ranks. So what you see here, this program that is running redundantly on all those processes. So each of these processes gets the same return value for size, but a different return value for rank. Now after we've got hold of size and rank, we can use them, and I'm just printing them here, hello world, I am rank of size. And then the work is done and we finalize. Of course, this is not a program that does any useful work. There's no work at all. There's also no sharing of work, but at least it starts a parallel machine. It gets hold of size and rank, and every process prints something. Unfortunately, compiling and running an MPI code is not in any way defined by the standard. So you're on your own. You have to consult the system documentation to see how it's done. So first of all, headers and libraries must be found by the compiler. If you work with a compiler alone, then you quickly end up with a plethora of extra command line options for telling the compiler where to find this stuff. So this is why most MPI implementations provide you with so-called wrapper scripts, which are similar to compilers. They're called MPI and then some compiler name like MPI F90 or MPI CC. They behave like normal compilers or linkers if you don't use MPI with them, so you could just as well use them as your standard compiler. But the good thing is they know where to find the headers and libraries, so that's not something you need to think about if you use these wrappers. The names of these wrappers are not defined by the standard. They are also not normalized, or there's some common choices like MPI CC, but you never know. So that's something you have to look up. Running the code is just as badly defined. The details are very implementation specific. A whole collection of typical wrappers exist. The oldest one is probably MPI run, but there's also MPI exec. On Cray systems, it's called AP run. On IBM systems, it's called POE, and there are some others. So again, documentation is your friend. So I'm assuming here that we're on a standard cluster with, for example, an free implementation of MPI, OpenMPI, where the C++ MPI wrapper is called MPI uppercase CC. We use it like a normal compiler, so our code from the previous slide is just compiled with MPI CC minus O hello, hello.cc, and then we run it with MPI run. The simplest argument we can give an MPI run script is the number of processes we like to run. In this case, 4. So NP4 means we want to run 4 processes. Remember, I'm not specifying here where these processes should be started. So I don't know whether they're running on the single node, on the current node, or on 4 nodes of my cluster. That remains to be seen. So if the program starts, it runs and it prints what I want. And just like with OpenMP, of course, the order of the output is undefined because I've done nothing in the program to make sure that the order is in the order of the ranks. So as I mentioned, the details of all this are very implementation specific. Where and how are processes started? How many processes per node? Where are they put? Can I set the process core affinity? Where does the output go? Now in our example, the output from the individual ranks just was only simply piped to the console of the starting process, the starting shell, but this could be different also. Another question that's important is, do I need a shared file system? So my home directory, or the directory in which I start the MPI program, does it have to be shared across all the nodes that comprise the cluster I'm running on? Or is it possible to have local directories there? These are all important questions, and they are not in any way defined by the standard, so consult the documentation. Our simple Hello World program didn't actually do any communication, but communication is like the core of message passing, so we have to deal with that first. When I communicate a message from one process to another, there are a couple of things that have to go with the message. We call that the message envelope. And this collection of information is just this is the stuff that you also write on the envelope of a letter. So which process is sending the message? Who is sending? Where's the data on the sending process? So a sending process has an address space, and I have to specify where the data is that I want to send. What kind of data is being sent? I told you in the beginning that MPI is designed for heterogeneous systems. So how data items are stored in memory may depend on the architecture. So I have to give MPI the information which data types are there to be sent. And of course, how much data is there? How long is the buffer? At the receiving end, of course, I need to know which processes have to receive the message. Where should the data be left? So is there a buffer or an array of sorts where the message should be copied? And how much data is the receiving process prepared to accept? Of course, I have to prevent a situation where the received message is bigger than the space that is available for that message. Of course, sender and receiver are separate processes, so they call also different parts of the library, so they must pass their information to MPI separately. The green stuff is the sender's part, and the blue stuff is the receiver's part. In MPI, processes communicate by sending and receiving messages, and an MPI message is an array of elements of a particular type. So we have a sender process which has rank I, and a receiver process which has rank J. There's an array of objects, of elements on the sender process, and by sending this to the receiver, I make a copy of the data into the receiver's process space. Of course, the sending data is not altered in any way in this process. The data types I can use for the individual elements of these arrays, with those data types, MPI is quite flexible. Of course, we can use the standard, the basic data types that the base language provides, like doubles and integers and floats. But we can also define our own data types. They are called MPI-derived types, and that's actually a very powerful and flexible method of defining communication, which we'll cover in the advanced MPI part. Here's a list of predefined data types that you can use in a C program. Of course, a similar list exists for Fortran. So you recognize your old standards like float and double. Float is called MPI float. Double is called MPI double. Bool is an MPI C bool. There's unsigned integers and unsigned long and signed versions of those. So all the stuff that you use as data types in C is actually available in MPI. This list is not comprehensive. There are a couple of more and you can look them up in the standard. There's one special data type, which is MPI byte, and this is defined as 8 binary digits. So if you insist, you can always send all your messages with a type of MPI byte, but you will lose some functionality, especially when it comes to data conversions in heterogeneous systems. So this is generally not recommended. In MPI, there's one concept that's quite important, and this is data type matching. So if you send a message, the same type of data must be sent and received on both ends. So this is a requirement for the message to be transmitted. If you have a heterogeneous system where different parts of the system choose different ways to store data, then the data type conversion is automatic. A typical example for this is big endian and little endian systems. In a big endian system, a multi-byte data structure is stored with the most significant byte first, while in a little endian system, the least significant byte is stored first, so with the lowest address. MPI supports using these kinds of systems in the same MPI program. So if you transmit a double element, for example, which is 8 bytes, from a little endian to a big endian system, MPI takes care of the conversion. This is quite convenient if you have that kind of setup. The simplest way to communicate in MPI is blocking point-to-point communication. And there are two terms here, point-to-point and blocking. Point-to-point is a simple concept. There's always one sender and one receiver, both identified by rank. It's as simple as that. Blocking is a little bit more complicated. The way that MPI defines the term blocking is not the standard definition of blocking, which means if the call returns, you're done. Okay, this is not the meaning that MPI attaches to the word blocking. One might call this choice of words unfortunate, but that's just how it is, and we have to get used to that. In MPI, blocking means that after the MPI call returns, the source process can safely modify the send buffer. So whenever the MPI send call returns, you can safely reuse the buffer and do whatever you want with it. The receive buffer on the destination process contains the entire message after the call has returned. So this may seem trivial to you. Of course it contains the entire message, but you will later see that non-blocking has a different semantic. So this is the semantic of blocking. You can safely modify the buffer no matter whether you sent something or whether you received something. Here's the syntax for the standard blocking send in MPI. We have 6 arguments. The first one is probably the most important one, is the address of a send buffer called buff here. In C it has a data type of void pointer. The count argument is the number of elements comprising the message. So this is the exact count of elements that we want to send. The MPI data type is one of the predefined types that I showed you a couple of slides before. The destination is where the message should go, so the rank of the destination process. The tag is an additional number, like a label that you can attach to the message. You don't have to use it. If you don't want to use it, you can always set it to 0. But sometimes it comes handy if you want to distinguish different kinds of messages, like messages transferring data or commands, and then you can use the tag to distinguish these flavors of messages. And of course we need the communicator, because it has to be known which communicator the destination rank refers to. After the MPI send call returns, since it's a blocking send, the send buffer can be reused in any way you see fit. However, once the send call returns, you know nothing about the destination. The message could be stored in the local process and still be sitting there waiting for being transmitted. It could be in transit somewhere in the network. It could be already at the destination process, but not in the receiving buffer, or it could be actually in the receive buffer. You don't know. On the other side of this process, we need a receive, and the standard blocking receive is called MPI receive. Of course, we again need a receive buffer, which is again a void pointer, then a count argument. Now, in case of the receive, the count argument is not the size of the message, it's the number of elements that fit into the receive buffer. This is a way for MPI to determine whether the message to be received will overrun the end of the buffer, and this cannot happen, this shouldn't happen. So here we specify the number of elements that can be received at most, so that fit into the buffer. Again, we have the MPI data type. Of course, we have to specify who should be sending, so who are we receiving from, the message tag, and the communicator. In addition, we have a so-called status object, actually a pointer to an object of type MPI status. And this is very important because after MPI receive returns, there are some things you might not know. So at completion, the message has been received successfully. So this is the semantics of the receive. You can use it in any way you like, but the message length and probably also the message tag and the sender might be unknown. Now, why is that? The reason is that MPI receive accepts so-called wildcards for the source and tag arguments. Instead of specifying a definite source rank, you can just say MPI any source, and instead of naming a specific tag, you can just say MPI any tag, which means you're able to receive or you're willing to receive from anyone and whichever tag the message carries. Now, if you do that, the actual source and tag that are attached to the message are available in the status object. So the status object has to be initiated like here. The MPI receive returns, and in this case I'm pulling all the stops, so I'm using wildcards for the source and the tag, and that's actually the reason for the status, or two of the three reasons for the status object, that I can get hold of the source and the tag afterwards. Now, after its receive returns, of course, the tag and the source are known, and I can request them by accessing the components MPI source and MPI tag of the status object. Now, the third thing that might not be known when MPI receive returns is the actual length of the message. And this can be obtained via MPI get count. MPI get count also gets the status object, now here in the form of a pointer. It needs to know about the data type in the message, and the count argument is actually an output argument that gives us then the actual length of the message. So MPI get count, address of the status object, data type, and address of the count variable. This is how you get the length of the message. Now, I mentioned before there are some conditions in MPI for when a message can be reliably transmitted. And there are actually definite rules, and you can read about this in the standard a lot, so I try to summarize that on this slide. For a communication to succeed, the sender must specify a valid destination. It must, the receiver must specify a valid source rank or a wildcard. The communicator of the two must be the same. The tags must match. The message data types must match, and the receiver's buffer must be large enough. So this is the list of conditions it must hold. If any of these conditions do not hold, either the messages or the transmission will not match, which means the receiver will not receive the message that the sender sends, or there will be an error condition. This slide summarizes the beginner's MPI toolbox, the 7 functions that you always have to know. MPI init, it's like let's get going, initializes the parallel program. MPI com size answers the questions, how many are we? How many ranks are there? MPI com rank lets you know who am I, so what's my rank from the point of view of a single process. MPI send is the basic blocking point-to-point send that sends an array of data to someone else. MPI receive is the basic blocking MPI receive function that receives data from some source or from anyone. MPI get count answers the question how many items were actually received, and MPI finalize finishes off the parallel program. Remember that what we've covered up to now are blocking semantics, so the send and receive buffers may safely be reused after the call is completed. That you would probably also naively expect if you do MPI programming. MPI send must have a specific target and tag, of course, because I have to attach something to the envelope that lets the library know where the message should go. MPI receive does not, however, so MPI receive has more freedom. That's why we need things like MPI get count and the elements of the status object to get hold of the sending rank and the tag. So far, we haven't covered any means of explicit synchronization, so this is not part of the beginner's toolbox. At the end, let's look at a simple example. And this is just more than just hello world. It actually comprises work sharing. It's parallel integration. We assume that you have a function f and you want to calculate an integral a to b f of x dx. The actual integration numerics is implemented in the function integrate. We presuppose that this function already exists somewhere else. Now the general strategy is here to split up the interval from a to b into equal and disjoint chunks and compute partial results in parallel. So this is what is done here. Everything that's green in this program is MPI or MPI specific. The splitting up of the interval is in purple. So here we calculate the start and the end limits for the local integration space. So starting point, of course, is a plus rank times size of the integration space per process, and the end is just the beginning plus the interval size. And then we call the integrate function to integrate over each process's own chunk. Remember, this is called by all processes. Starting from the beginning, n processes are running. Everyone calculates its own integration space. Everyone calls integrate on its own. And all the variables and data we see here are non-shared. They are local to each process. So after the psum function returns, the actual work is done. The problem is that we have partial results now on each process. So we somehow have to find a way to collect these partial results to get the final integration. This is done using MPI, point-to-point communication, of course. So we have a kind of master worker scheme here. Rank 0 is the one that collects the partial results. So if the rank is 0, which we determine here with this if condition, we assign the local result psum to the global result variable res, and then we have a loop here from 1 to size minus 1. This is a loop over all the communication partners, over everybody else that's part of the communicator, and this of course are the ranks from 0 to size minus 1. We receive whatever they send in our local receive buffer temp. The array length is one element because everyone has a double precision variable that it stored its local result into. The data type is double, of course. The rank of the source is I, which is our loop index here. The tag is not used, so we set it to 0. And of course, we are in the world communicator. Since we're calling an MPI receive function, we always require a status object, which we have instantiated right at the beginning of the program. After the receive call returns, the partial result from rank I has been stored into the buffer temp, and then we accumulate it into the global result variable. After that, after the loop is done, every slave rank has sent their data to the master, and the result can be printed. Now the else branch of this if condition, this is where all the ranks go that do not have a 0 rank, so all the slaves. They send their local result psum to the master, to rank 0. So the send buffer is psum, message length is 1, data type is double. The rank of the destination now is 0 for everyone. The tag is again 0 because it's unused, and the communicator is MPI, world. This is a typical pattern of a master-slave program where one one process is designated as the one who collects the data from the others and somehow fabricates a global result. So, of course, this is a very simple program, and we solved the problem of parallel integration using very simple means, namely the basic MPI toolbox. So some comments are in order. First of all, gathering results from a process or from many processes is a very common pattern in MPI, and there are many more efficient and elegant ways to do this. So MPI gives you a lot of infrastructure to gather stuff from other processes. You may have noticed that this is a reduction operation because OpenMP has a very similar thing, and of course MPI offers more efficient and elegant ways to do reductions, of course. In our program, the master process waits for one receive operation to be completed before the next one is initiated, and it scans the communication partners in order. Of course, there are more efficient ways to do this, and well, we'll see about them later. As I mentioned, master worker schemes are quite common in MPI programming, and there's nothing wrong with it unless you're creating a bottleneck at the master. Of course, it may be that in some settings the number of workers is so large the master is overwhelmed with communication requests, and this could lead to bad performance and bad scalability. So in highly scalable programs, you might want to think about a different pattern from master worker. We also did not do any error checking, which is also a general pattern with MPI programs. And it's true. This is because debuggers are often more efficient if something goes wrong. And parallel debuggers are available. So there's actually debugging facilities that let you start parallel programs and step through the instances of the parallel process, instruction by instruction, command by command, to find the problem. And finally, in our program, every process had its own result variable, but only the master process actually uses it. So this is very typical for MPI codes. This means that n-1 processes actually instantiate the result variable, but only one uses it. In this case, it's only 8 bytes, so it's not an issue, but this may be a problem in more complicated codes that only a few or a small part of the MPI communicator actually uses some part of the data, and this has to be taken care of if it occurs. So lots of things to learn, lots of things to do. We'll see about all of them. Before we conclude, some useful MPI calls. You might remember that in OpenMP we have timing functions. MPI is the same thing. So in MPI we have the function MPI wtime, which returns a current timestamp. So it only makes sense if you call it twice and calculate the difference. MPI wtick gives you the solution of the timer, so the number of seconds between one tick and the next, so you can determine whether a certain time span that you might have measured is sensible or not. A third interesting function is MPI abort. MPI abort serves to abort all tasks in the specified communicator and deliver an error code to the calling environment. It makes, according to the standard, a best effort to do that. But however, there's no guarantee that it won't end up pulling all processes in MPI com world down. So it's actually a last resort. If possible, if an error condition occurs in your program and you detect it, try to shut down the program using the standard facility, which is executing MPI finalize. All right, so here's a summary of our beginner's MPI toolbox. We learned how to start up and shut down the parallel program with MPI init and MPI finalize. We learned how to MPI tasks or processes are identified by their rank and how to obtain the number of MPI tasks with the MPI com size. The startup of processes, and this is very important, is very implementation dependent. There's nothing that standardizes this process, so it could be different on every new cluster that you encounter. Simple blocking point-to-point communication is done with MPI send and MPI receive, and that's actually the basic functions that you need to solve any MPI problem. These two functions have blocking semantics, which means the buffer can be reused as soon as the call returns. Always think about message matching, so things like sender and receiver ranks, data types, and tags must match to be able to transmit a message at all. And there's a couple of facility functions, most important timing functions that let you that ease your life with MPI. Thank you.